Right? So we now interpret this this E here as an energy term. This eigenvalue, or this E, we now think of as energy. Okay? So when we have this Schrödinger time-independent equation here, and when we try to solve it, effectively we're trying to find two things. One is, what values can this E take so that this gets solved? And you'll see, we'll do this several times, quite a few times. So you'll get accustomed to solving an eigen equation of this form. In this case, it's a Schrödinger equation, time independent. So one thing you need to do is to find particular values of E that allow this equation to be solved. That's one thing. And the second thing is, you need to know what these U's are. These, they're wave functions, but depending only on the position now, not on time, right? U is a function only of x, not of t. So summarizing, with your time-independent Schrödinger equation, you try to solve this equation to find two things. What values of E here give you a solution? And what are the wave functions, U? So you need to solve for E and for U, right? Now we'll start doing it, and I'll just start here at the bottom here, because I ran out of board as usual. Doing our very first example of doing that, you're finding what E is and what U is, or what they are, because usually more than one, all right? Okay, so in general, sort of, when you have a time-independent Schrödinger equation, what do you do? How do you go about solving it? Well, and we'll do case after case, quite a few. But what's in common? What they all have in common is that you're given a potential for a particular kind of problem. Like here we'll start our first example, where the potential, your V, is given. That might be a harmonic oscillator type problem, or it might be a particle in a box, barriered type box type problem, which is this one. And so you're given your V, so you know what the V is for your equation, and then basically you're just solving a differential equation, right? Like I said a bit before, wave mechanics to a large extent is just solving DEs, differential equations, right? So think of wave mechanics in those terms, like as a mathematician almost. You're just solving DEs, a particular kind of DE with certain trimmings. That's physics, right? But that's what it boils down to. Okay, all right. So you have a particular kind of problem. You know the potential V. So you plug that value V into your time-independent Schrödinger equation, and then you just solve the differential equation. That's what it boils down to. So in other words, you have to find what these energy values are, that come out of the mathematics, and the wave function. And the wave function gives you the probabilities. Well, you have to square it, the probability densities. But if you know the densities, you can calculate the probability that the particle will be found in a given volume. You just take the integral. You integrate the probability density, which would be this U squared. Okay. All right. Now, I was saying a bit before in the previous session, the really interesting thing about this kind of differential equation is it's an eigenvalue equation. So you'll have an operator, eigenfunction, equals eigenvalue, some constant, times the eigenfunction again. So L U equals some eigenvalue, let's call it lambda U, right? Of that form. That's your general eigen equation format. It looks like this. Here's your eigenfunction, that's your eigenvalue, and that's some sort of a differential operator usually. Right? Now in Schrödinger's case, the differential operator is, well, it's this, except for the U here. Oh, plus V. Yeah. All right. Okay. Now, as I was mentioning a bit in the previous session, the really interesting thing when you solve this eigen equation, this Schrödinger equation, is that quite often the E's that give you a solution, your eigenvalue. This is now an eigenvalue. Don't be confused with a wavelength. Right? It's just a. Don't be confused by that. It's just a eigenvalue. So for a given problem that you're trying to solve, in other words, you're given the potential of what kind of you're given some formula for the potential. Then it's often the case that there are only certain discrete values of E that allow a solution. So by solving Schrödinger's equation, you actually predict discrete values. In other words, quantized values. And hence, Schrödinger's equation gives you, in a sense, a quantumized or quantized mechanics. Right? It just sort of falls out of the mathematics, which is very nice. Right? So I've written here. Sometimes E must be discrete. It can only take on discrete values, not continuous values. Right? For solutions, your eigenfunction, for your solutions U to exist. Right? It just comes out of the mathematics. So from Schrödinger's equation, you deduce just a consequence of the math of the solutions of eigenequations, Schrödinger's equation, that only discrete values of E are possible in certain cases. Right? So wow. So now you can imagine how Niels Bohr felt, because in 1913, I think it was, he was saying his model of the atom was that the electrons that were going around the nucleus, he took Rutherford's model of the nucleus of the atom and put the nucleus in the center and had electrons going around the nucleus only in certain orbits, other orbits not allowed. And here, that was his picture. And here now you get mathematically the prediction that only certain energies, and hence if you know the energies, and hence only certain wave functions are allowed. It just comes out of the mathematics of Schrödinger's equation. So you can imagine Bohr was absolutely delighted by this, right? He had his old idea now, more than a decade old by that stage. Let's see, Schrödinger, when did he do all this stuff? 25? 26, 1926, 25, that sort of time frame. So 12, 13 years after Bohr made his famous model. So there's a bit of a story here. So Bohr invites Schrödinger to Copenhagen to talk about, lots of things. And Bohr had a million questions for Schrödinger, and Bohr was a very formidable intellect, right? He was a match for Einstein. Those two later were like two titans in one of the greatest intellectual debates of the 20th century, over the very core, the nature, the heart of quantum physics, over the nature of reality. And essentially Einstein was determinist. He wanted quantum mechanics to be modified to make it deterministic. And Bohr thought that was just totally wrong-headed, that Einstein was just stubborn and silly. And so those two just at it like this for decades, literally. Anyway, so Schrödinger arrives in Copenhagen, picks up the local germs, gets a cold, very bad cold, and poor old Schrödinger just got hammered by Bohr. Bohr just persistently saying, but how can there be quantum jumps, and just pummeling Schrödinger for questions, philosophical answers to deep interpretation questions. What is this psi function? For Schrödinger, he had a somewhat de Broglie-like image in his head. For him, the wave function was some sort of physical thing as well, to some extent. Maybe not as strongly as de Broglie. And after days and days of pummeling questions from Bohr, Schrödinger got really sick. He had a really bad cold, and eventually he got so sick of the debate, he left in a bit of a huff, and thinking, he regretted becoming a quantum mechanic in the first place. So Bohr really gave him a hard time. Anyway, okay. So, but Schrödinger made a huge contribution to quantum mechanics. Now, okay, so we have this equation.